they can store more ions than conventional graphite-based anodes, and unlike graphite-based batteries, silicon-based batteries feature a higher energy density. However, some existing lithium-ion battery manufacturers are using a small portion of silicon in their batteries, which limits their performance. By contrast, GDI's approach uses 100% silicon in its batteries, resulting in much better performance and reduced risk of lithium dendrite formation. Moving on, how can silicon anode batteries be applied into Tesla's EVs? Tesla definitely confirmed that
have silicon in the cars that you're all in right now are involved highly engineered, expensive materials in the scheme of things. Now, they're still great and they enable some of the benefits of silicon. They just don't enable all of it and they're not scalable enough.
Actually, the first production of the Tesla Model S vehicle had 5% silicon mixed into the graphite, and until now, most companies still remain at that 5 to 10% range. Nowadays, however, Tesla is using a whopping 10 to 15% of silicon, adding it into the anodes of the battery to boost capacity and energy density. The reality is that all cars are affected by extreme temperatures, but EVs are particularly susceptible to extreme heat or cold weather. For Tesla's electric cars, the battery performs best when it is within 20 degrees Celsius, and the reaction increases from 122.22 to 127.07 degrees Celsius. Therefore, silicon anode batteries can work well at much higher temperatures than 2.3 times when compared with lithium batteries. Since the lithium battery has a safety level only from 55 degrees to about 80 degrees Celsius, silicon anode exhibits better rate capability resulting from faster electrochemical reactions and fast ion migration in the electrolyte and electrodes. In temperatures above 80 degrees Celsius, the cell begins to experience damage, and anything above 130 degrees will result in the constituent parts of the cell melting and potentially starting a fire. The side reactions in this case become severe, resulting in a fast capacity decay. On the other hand, to have such a battery, the producers used both platforms and both models in each platform, with all of them using the same inverter that uses 24 silicon carbide devices, which have 2 silicon carbide die in each device package. These 48 silicon carbide devices have a 400-volt system at a simplified 160 kilovolt ampere power. In recent years, Sila Nanotechnologies, which was founded in 2011 by a group of ex-Tesla battery engineers and a Georgia University materials science professor, have been working on silicon anode technology, which was first developed at Georgia Tech. They spent the last decade developing materials and next-generation silicon anode chemistry for lithium-ion batteries called nanocomposite silicon. And for the last part of today's episode, what is the outlook looking like?
So I think it's now ready for the industry to really take it to the next level in terms of scale up the production
for silicon anode batteries. In the final quarter of 2022, startups raised nearly $500 million. The global market size for silicon anodes is expected to grow from $1.2 billion in 2021 to over $208 billion by the end of 2031. The remarkable characteristics of silicon make it the most capable candidate in the battery industry. So I think it's now ready for the industry to really take it to the next level in terms of scaling up the production. It really ups the game because the energy density and the capacity of the battery is not increased only by a couple %, but by leaps and bounds.